It's in there.
She won't forget about it because it's your computer. But...
All right. Will you die?
Nope, I won't die. I'm not kidding either.
Yeah.
Yeah. All right. Okay. Zoom is on. Screen is on. iPad is on. I think all the technology is in order. So I'm hoping this will be kind of a short-ish lecture where it's mostly going to be practical. So the topic is going to be calculating particle size distributions. And the reason that we want to do that is because we're right now sort of building a repertoire of optical measurements and IoT measurements that we can use to give us proxies for particle size distributions of particles in the ocean, right? But we want to validate those against something, and we want to think about the meaning of those particle size distributions for the actual biogeochemical processes we might be interested in. And so what we're going to do is just take a little side tour into, if you have actual measurements of something that is, particle count measurements as a function of size, or imaging flow cytobot, IFCB data, or you've taken your phytoplankton sample and you put it on a slide and you stuck it under the microscope and counted it, or you've got a UVP, an underwater vision profiler, and you're using a camera to image the particles in the water. You've got all of these direct, or more direct anyway, measurements of particle size. How do we take that information and condense it into a form of particle size distribution and maybe model it in a way that's really more useful to relate to the IOP-based proxies that we're developing, if that makes sense. So we're gonna kind of go over to this, how do we deal with particle size data, just for a little bit. And at the same time, I think I'm gonna give a little bit of a simple MATLAB example, because not everybody is a comfortable MATLAB user. Some people program in other things, but I know a lot of codes you guys are getting are in MATLAB, and some people haven't coded a lot at all. And so it's just going to be kind of a simple approach to the one particular task. So I want to start off with a little bit of a knowledge survey, I guess. When you guys think about the types of oceanography or the types of environmental science that you're interested in, what are some particle size dependent processes that are important? Why would you even care about particle size in the ocean?
Trophic interactions.
Trophic interactions, yeah. So big things eat smaller things, and so on and so forth. Yep.
Food chain length and size.
Yep. How complex is your food chain? Yeah. Carbon export. Yeah. So that's one of my favorites. You're thinking about sinking particles and how they transfer carbon into the interior of the ocean. That may or may not be a size dependent process, but at least theory tells us it should be. Yeah. Okay, so how particles are maybe responding to the fluid environment that they're in as a function of size, yeah. Sedimentation, yeah. So sort of more generally, I think carbon export might be kind of a specific case of that, but if you're looking at turbidity in a river channel, right, or bed, transported sediment along a bed, highly particle size dependent process. Yeah.
Water mass tracer.
Water mass tracer, yeah. And there was something else that I heard in the other corner over there. Nutrients. Nutrient dynamics, okay. So sort of related to maybe the phytoplankton community that might be influencing the nutrient dynamics. Okay. All right. I'm out of space, but is there something really important or question?
Like the scattering, the word scattering. Word scattering in like an active system, maybe.
Okay, so interpreting LiDAR data. Okay, so So it kind of feeds back onto some of these optical methods that we might be using. And if you're interested in the optical methods for their own sakes or for some other purpose, then the particle size might indirectly be a really important thing to have handle on. Yeah, so lots of reasons. Ooh, that didn't show up as well. I thought orange would be the best contrast against blue. I'll change colors. That's horrible. I don't know. Can you see the words, Emmanuel?
Not pretty long.
Okay. I'll type it up maybe for the real version that gets posted later. Okay, so those are some processes, and I'm sure you guys have many that you're thinking of that are relevant to you, right? Where particle size itself is important. So then what are some methods that we have to directly measure particle size? I kind of spoiled it by talking about a few of them at the start, but yeah. Flow cytometry, right? So line up all the particles in a tiny tube and shoot them past a laser.
Is that right? You measure the size.
Hmm?
You don't measure the size, though, right?
Well, you do actually, if you shoot them past a camera, you do. I mean, insofar as taking pictures of something is a direct measure of particle size. Yeah, closer than,
If it's picture, it's not,
yeah. So imaging,
imaging.
flow cytometry, that's an important distinction. Yeah. Otherwise, we're using an optical proxy, right? So laser particle analyzer is probably measuring the diffraction by the particle. So that's actually a proxy. I'm just going to cheat and jump forward and put it over here on this side, which is where I'm going to put our optical proxies for particle size that we know about. So that's one where we're looking at light scattering and using that to infer particle size. But if we're looking at particle size directly or more directly, microscopy, yeah. Put them on a slide and count them. Yeah. UVP, yeah. So can I just write UVP as an underwater vision profiler? It's a submersible camera that takes pictures of relatively larger things, like 100 microns-ish and bigger. Yep. Do we have any people who are kind of have geology backgrounds? So, okay, so say what you said again. Granulometry. Okay, so like looking at the grain size via sieving, maybe. Yeah. Okay, yeah, so sieves. And I'm just going to add filters on here since we have had some quality time with those recently, right? If you can use a series of filters and separate things and then somehow analyze without the filter. Yeah.
Sediments and particle cups.
Sediment and particle cups.
Tracks.
Tracks. Yeah. So yeah, so sinking velocity separator trap maybe could you could infer things about size, but that's more sinking velocity. Tracks capture everything, right? And I'm a sediment trap person, so that's why I'm like, yeah, but you can collect them and then use a particle size method or microscopy or something, right? Or yeah. Actually, nobody has said Coulter counter yet. Has anyone used a Coulter counter? Or read about one maybe? So no, you're right. It's not, but it's not an optical proxy either. So maybe we should say not directly, but not optical, not optical proxy. We are having some imaging methods, which are technically optical. I'm sorry, you're seeing the limitations of words. Okay, sieves, filters, electrical impedance is the principal, impedance is the principle that a Coulter counter works on. Looking at the resistivity associated with a single particle passing through a tube. Is there any other? Yeah. Do you have any favorites that we should add to the list that people might not have thought of for a while?
There's one that, you know, the dynamic line scattering.
That's an optical proxy.
That uses, that includes for these.
The fluctuations.
Molecular motion.
Yeah.
Due to size, there's a effect by size, like from.
Okay. Is data potential is more of a, I guess those are all getting pretty indirect.
And this flow refraction.
Yep. Which is sort of like a filter, but not really. We'll add ultra cross flow. Has some options for filters. Okay. All right, so particularly with all of the camera-based imaging sensors that are out there, I mean, someone in the last few days, and I'm sorry, it's flowing together a little bit, made a really good point that we are exploding in data in our field these days. That was Wayne, I think. That, 10 years ago, it was hard to come by data points. Now, so much data. And part of the reason for that is these imaging sensors. We have so many pictures of the particles. And so now we need to connect that to our IOPs. We need to connect that to our remote sensing proxies. We need to connect that to the things in the ocean and the environment that we're interested in. And so that's why we're going to talk about particle size distribution. All right. So I'm going to start by going back to 1972 to an interesting paper, Sheldon et al., which postulated that first order, there's roughly equal amounts of stuff, of matter, in particles in log-spaced size bins in the ocean, going all the way from bacteria to whales, right? But if you look at the amount of stuff in the bacteria size pool and the amount of stuff in the whale size pool in log-spaced bins, it would be about the same. And this, which I think Emmanuel has already said, is consistent with a number size distribution that has a diameter raised to the power of -4 dependence. So ND here is number of particles as a function of diameter. E. And I will use the same terminology in a little while. Okay, so it's consistent with this d to the -4th power law spectrum, which you've seen this power law spectrum now cropping up all over the place. One of the reasons that we kind of like to try and make proxies for particle size with wavelength dependent IOPs, right? So this has this postulation that we've got this sort of flat mass distribution in a log sense in the ocean has ecological implications, right? It's sort of saying there must be processes that are moving mass up and down the size spectrum in a steady state way, if this is actually true, right? So it's kind of just an interesting thing to think about, and it's an interesting paper to read if you get a chance. It's old. It was from before I was born. Here I'm showing you another example. These are some figures from a paper that was published the year I graduated from high school. And this is by George Jackson and colleagues. This is another one of those really a lot of work, but really useful intercomparisons of method studies. So in this case, a bunch of people got together with all their custom built high specialty like particle imaging and particle size measuring devices and stuck them all in a lake together and measured the particle size distributions using these different things and then tried to merge the particle size spectra. And so this is another really great paper to read if you're interested in these method intercomparisons and issues that might crop up when you're trying to measure particle size distributions. The figures here are all showing, again, the number size distributions, the number spectrum of particles. And I'll talk about the units here in a second. They're a little different than you might think. So it's the log of the number spectrum versus the log of the particle diameter. They're all set up the same way. They don't all have the same limits. They're different instruments, and each one has this difference in shape, right? So there's a couple of things to think about when you're measuring particles. First is, what's your instrument sample volume? How much seawater are you actually counting particles out of? Are you missing really rare things because you've got a tiny sample volume, right? Or are you doing a better job of capturing the true size distribution with a large sample volume? So that's one thing. You guys can kind of see this. There's very fine dotted lines here. You see those? So those are for each instrument. That's this detection limit on the large end. So that's basically saying, you can count one particle, right? What's the one particle limit for each size of those? So all of those different instruments are kind of peeling off where they hit the dotted line in the different size ranges. Okay, so it's saying you can't measure less than one. if you're, as a function of your sample size. The other thing to think about is on the small end, right? Small end of your particle size spectrum, what's the smallest particle you can detect? And what happens when you get to that limit? So if you're using an optical imager, your lens is going to be limited at some point by maybe your camera resolution or the wavelength of light, maybe you're at the optical limit of resolution. There's certain particles you just won't be able to resolve because they're just too small. So when you get down to that end of your particle size spectrum, you start to see things like this, right? Where your spectrum starts to roll off and get noisy as you get really small. So knowing where that is for your instrument so that you can treat properly the data that are coming from that part of your size spectrum, also really important. So those are kind of two important factors to think about when you're interpreting particle size distribution data. How big is the sample volume, and what's the least that you can detect in terms of numbers at that within that volume, and then what's the smallest size that you can detect, and what do your data look like when you reach that limit. There are actually some instruments where the counts increase when you get towards that limit, and then a lot of imaging ones, they decrease. There's a decrease. Okay, so leaping forward in time, I'm just going to show you one example that also illustrates this power law size distribution slope. And this is from a really more recent paper, just 3 years ago. B.B. Kale and Angelique White looked at the particle size distributions of particles in the water column and in sediment traps at the Hawaii Ocean Time Series station, which is in the North Pacific subtropical gyre. And they used two different methods. They used near forward scattering. So they used the list, which Wayne talked about this morning. And then they also used an imaging flow cytobot, which you guys cut out those pictures from on Monday night. So they have these two very different ways of measuring particle size distribution. And they fit all of their particle size data to this function, this power law function, which we're going to do in MATLAB here in a second. And this is basically, again, the number of particles as a function of diameter equals the number of particles at some reference diameter, often arbitrary, times the ratio of the diameter to the reference diameter raised to some power. And psi, our Greek letter, is often what gets used there. I think in my code, I use capital B. That's nice. Easier to type. But this power law exponent here is what's up there in that equation. So the units of ND are going to be the number of particles usually per volume, although you're not worried about volume, you can leave that out. I'm just going to say per liter, per volume, if you're going to do this, a fit to these data, per width of the size bin. So let's say we've got particles that we're measuring their diameters or their sizes in microns. And we'll talk about why that's important here in a minute. But you have to do that. You want to compute these. L is, it's a volume, it's a liter.
L is the volume.
Yeah, so this is actual units. Yeah, so.
I would not have a minus one. So like that.
Oh, yeah, you're right. Sorry. Thank you for catching that. So number per volume per bin width is what those units go with. Okay. So if I back up a slide here, the units on the Jackson et al. Figure is number per centimeter raised to the fourth power. And that just aligns with what I showed you here, right? Number liter has a length cubed dimension, and the bin width has just a length dimension. So all together, you can get a length raised to the fourth. So that's like a differential power law spectrum. Okay. All right. So anyway, this is an interesting paper to read too. I'm not going to go into a lot of the details of it, but it's just sort of an example that illustrates a lot of the variability that you can see in power law slopes just in one place, depending on what part of the particle pool you look at. And we see the same thing or similar things with really different instruments, which is useful. Okay, So what we're going to do next is work through a simple example, just taking some raw IFCB data. And I don't use the imaging flow cytobot data at all. I have no preconceptions about anything. So I'm going to take some raw data and read it in. And we're going to bin it into size classes, visualize the uncertainty, and fit a power law model to the data. And hopefully demonstrate a relatively straightforward use of a MATLAB script to do this, where we go through each step individually. I'll make some very simple figures. So if you're not a MATLAB user and you want to see something that someone built in a sort of slow, simple way, which is how I do most of my coding. Actually, I do it fast, but it's all simple. Rather than, there's some complicated tools you guys have access to as well. So this will be a little different. There is a regular and also a live script version that I'm going to be using up here on the screen. They're both posted in the student share drive in the lecture 9, whatever number we're on, PSD folder. So if you want to follow along, you can, or you can just take it out and look at it later. You do need to grab the whole folder. There's a data file in there. There's an M file. There's 2 M files and a live script file. And you need to have all of that in the same folder for it to work. Okay, so now I need to stop sharing that and switch over to the MATLAB. And this is my first time teaching with MATLAB live scripts, so I hope it works. And if it doesn't, put it on a sticky note or just tell me. I think it will work better than my showing you my screen. Here it is. You really can't see that, so I'm going to make this much, much bigger. All right. Actually, maybe there's a way to, yeah, be normal and then zoom in. Okay. Is that legible?
Yeah.
Yeah, fantastic. Okay. So, so this script is put into the sort of presentation format, but just like code blocks in a regular MATLAB script, you can click in any of these blocks. And on a Mac anyway, it's Command Shift Enter to run each block is what I'm going to do. And it's something different on a PC. Yes. It's in, so there's a folder. It's in the student share drive. So I think it's where you guys are like putting your data and stuff. I just dumped it there because I knew you all knew where that was. And then I called it lecture 9 PSD codes or something like that. Find it? Okay, so you need everything in that folder. It all needs to be in the same location on your computer. And you have to get into it in MATLAB. Okay, so there's a data file that you will pull down. That is this thing right here. So it's a CSV file. It downloaded it straight from the IFCB website dashboard. And so what I've got here is just some code that's going to read that into a matrix called A. That's just going to be a big grid of numbers. And I don't even need all of them. I'm just going to read the whole thing in though. It's got one header line. So if you open up that CSV in Excel, you can see what all of those say. And then from the dashboard, I read that this was a 3.994 milliliter sample volume that we're going to be looking at the data from. And I want things to be in liters, so I'm just going to go ahead and divide by 1,000. So that's all that does. So I'm going to click in this block and hit Command Shift Enter. And if I flip over to my MATLAB workspace, I've got all of that over here now loaded in. Okay. So now I happen to know, because I've looked through this already, that column 9 has the equivalent diameter from the IFCB. The actual projected area in square microns is in column 2, and the estimated volume from an interesting little algorithm that Moberg and Heidi Sosik came up with. They compute volume based on the distance of the edge from the center. It's a cool paper. I'm going to read all that in to variables that I've named usefully, and then also the number of particles. So I'm going to run this block. And I didn't stick a semicolon on the end of that line, so I didn't suppress the output. We can see that there's 3,393 particles there. So with any raw data set, the first thing you want to do is plot it and look at it. What is this data doing? How do I want to approach it? It's better to just look at your data before you start making decisions about how you're going to analyze it. So I'm just going to make a histogram. I'm going to give it the number of bins equal to the number of particles. So I'm just going to see it all. It's going to take a minute to come up. And label my axes and hopefully make everything legible. All right. And the figure will pop up here in just a second. I hope, yes. Right below that float block. That's why this is so cool. Okay, so what we've got here is our size distribution. What do we see about it? What are some things that jump out at you when you look at this? It's just a histogram with very, very, very narrow bars. What size are most of the particles? 20, 25 microns, right? So up to a point, we have lots of small particles in the sort of 20-ish. Sorry. Log normal, yeah, or at least there is a drop off and then a long tail, right? And then we just have a smattering of particles in the larger sizes. In fact, if I zoom in, which I think I can do interactively, can I? Yes. I'm just going to draw a box. Look at this. Okay. Those are one particle peaks, right? We just have a single particle, and a single particle. Emmanuel's shaking his head. You disagree. You're shaking your head at something else. Okay, great. All right. So we automatically should be, and I just double clicked on that to zoom back out. We should automatically be thinking, okay, we want to plot a size distribution or interpret size distribution information from this sample. There's not very many particles here. We already need to be thinking about what are our counting statistics in the larger bins. There's just not that many of them. Okay, so what I want to do is bin these particles into regular bins so that we can start to fit functions to them and treat them quantitatively. This was just a visualization here. And what I'm going to do is set up some bins. And because we have this lots of particles at the small sizes and then sort of log normalish thing trailing off to very few particles at the large sizes, we already might want to make the assumption that those bins should be log spaced, right? If we put them linear, we would have one very, very full bin and then a bunch of very empty bins that don't have good statistics in them. So to make log normal bins, I'm going to arbitrarily choose we want 10 bins. From our figure here, we can zoom in and say, let's make the minimum diameter 8 microns. That's about where it starts to fall off. Also pretty arbitrary, just picking it based on what I see at a first glance in the data set. And we'll make the upper size 200 because that's going to capture all of our large things. We'll see how it goes. So then I'll take the log, base 10 log of the min and the max. And I'm going to make a vector that goes from that min to the max and spaced out, that's between the colons here, by the number of size bins I want. So I'm going to get a vector that's got 11 elements, and that's the edges of all my bins. And then I'm going to calculate the centers of the bins, but I want the centers of the bins to be calculated in log space, right? If you do that in linear space, then your centers are going to be offset incorrectly. And then I'll switch back to linear space to get the bin edges and the bin centers. So I'll run this. And now I'm going to plot just where those size bin edges and centers are so that you guys can see them. All right, so here, the vertical lines are the edges, and the dashed lines are the bin centers. Okay, and this is a linear plot, right? So the bin centers actually offset a little bit from the actual center. Okay, so we're going to classify particles now into these bins that have their center dashed lines. Good so far? Okay. And I'm going to use the hist counts function to do this. You should maybe take a look at the MATLAB documentation or help to see some of the other things you can use with hist count. That you can, like, I'm going to tell it what the edges are of the bins that I want to classify into, but you could tell it how many bins you want, or you can tell it to output what bin each particle falls into if you want to do something with that information later. But here I'm just going to say, tell me the number of the bins with my data going in. So the particles, this is all of the list of their diameters, and then put them into bins with these edges. Okay. And I didn't suppress the output of this, so you can see the count in each of the bins. if I click these three dots, it'll actually give me a little array view that I can look at my data in. All right. And now I'm going to plot it. And so from here on out, I'm going to make two subplots in a row, one linear, one log, so you can see how that looks. And I'm going to try and make it look pretty and be the right size so that it's easy to see. So that's what a lot of this other stuff is doing. You can play around with, if you've not made figures in MATLAB, some of the parameters that. All right. So here's my first pass at guessing what bins to use for these data. So the one on, they're the same data, just number, not number per volume. I'll do that at a later step. And diameter in microns or log diameter. So what do we see? Were these good bins to have chosen? Yeah. Say it again louder.
The first three were pretty good.
What's wrong with the first three?
Don't fit the line you would expect in that. Right.
So if we expect a power law distribution, and I would say we can't automatically expect that, but if we do expect that, then yeah, they seem to fall off. And whether that's due to the IFCB or to the properties of the phytoplankton in the sample, I'm not an IFCB user, but I don't know for sure. But I will say that's pretty low, right? So it's probably the IFCB. We probably need to question our lowest bins. That might be getting close to its ability to resolve the particles, so it's not actually counting them all very well. What about the largest bins? How many particles is this? 10 to the 0, that's 1, 2, 3 particles. So we have 3 particles in our largest bin. It's not really great counting statistics. So we might want to adjust things, either the width, the number of bins, where our outer boundary is, so that we're grouping things in a little bit larger bins so that we have good statistics if we care about the large end. Or we can say, oh, we might just have to throw out that largest bin. We didn't count enough. There's not enough. Maybe we need to bin 12 hours worth of IFCB samples, add them all up, and then do our size counting. We just need more water to count that many particles.
Anybody have a sense of what are uncertainties in counting?
We're gonna get there. Yeah, but we can ask, I mean, what are our uncertainties in counting? Yeah. Okay. Yeah, so for an IFCB, you want to make sure your camera's in focus. You want to make sure you've got one particle when you think you have one particle. What about just statistically? We have a volume of 4 milliliters of water. There's some particles in them. There's lots of particles in the ocean, and we've taken 3 milliliters out. It's kind of random whether we get certain kinds in that 3 milliliters. So there's a little bit of randomness. We're actually going to use a Poisson statistics-based probability or uncertainty for the counting uncertainty, for the sampling uncertainty. And that's what we'll propagate into here, but that's going to be a few steps down. Okay. So I'm going to adjust my size bin edges. I'm going to keep 10 bins, but I'm going to raise my minimum diameter to 25 microns so that if this business is due to under focusing or sort of inability to really resolve the number of particles at these small sizes, we're just going to cut that off. And I'm going to keep the max diameter at 200 because we're shifting the bins to be a little bit larger. So there's going to be more stuff counted in our largest bins this way.
There's another problem the IFCB or you can trigger it.
Ah.
If you trigger a door, and you're smaller than less door,
Mm-hmm.
you're not going to have that.
Okay.
It's harder to get at this point.
So you're saying that the ones here might just be the phytoplankton, whereas once we get into the larger bins, or the other way around, we're missing the phytoplankton.
Even if the proportion of growth is the same, it's that growth is not trigger the camera.
Right, right,
Small.
right.
Same with scatter. It's scatter less. The smaller you are, the less you scatter.
Yeah.
And so if you trigger on scattering, you're not going to have the small.
Right. So that is a specific lower size and related bias of the IFCD,
Yes.
just like a microscope has an optical resolution limit. All right. So I'm gonna rebin with my new bins. And I didn't suppress all the output here, so you can see the new bin edges, the new bin centers. We still have very few particles out here in our largest size bins. We'll see what that looks like once we put in the counting uncertainty. That's partly an educational step I chose. All right, so we're gonna replot our rebin data. Uh-oh, how did I open the dictionary? That was a mistake. Okay. All right. So this is our new bin selection. This looks a little bit more reasonable, sort of power law-y. So we've got this nice power law looking slope on our linear plot. It mostly seems like a line, although there's clearly some deviations in the log plot. Okay. So now we want to put error bars on this. And we're going to assume that Poisson statistics apply in this case. So this is a Poisson distribution is basically the probability that an event will occur at a known mean, if it's happening at a known mean rate, right? So if you know the average, and then it's just a question of, do you happen to capture that random event in your subsample or not? And also you have to assume that each event is decoupled from what happened in the past, right? So if whether or not you catch a diatom in your IFCD is related to whether there's a bunch of diatoms that came before, like maybe a chain broke up and flowed through the tube, right? That would violate that assumption, but we're just going to, it's probably a fair assumption for most of the time, particles being subsampled out of the ocean. And so if you have this distribution, then the mean and the standard deviation of your subsample should be n, if you're counting things, right? N plus or minus the square root of n. So the error is going to be the square root of the number of things that you counted. Yeah.
Question just to make sure I clarify.
Yeah.
things correctly in my head. When you say standard deviation, what are you referring to? You said mean and standard deviation of n plus.
Right, so
Is
the
that
standard deviation is the square root of that. So
So-
the mean plus or minus like one standard deviation of events. You can calculate the standard deviation of the true thing as square root of n.
Are standard deviation and uncertainty different things or the same things? Or like the square root of n, is that your uncertainty or is that exactly equal to your standard deviation? Only statistic and then talking about the Poisson distribution?
Standard deviation has a meaning.
Yes, that's what I'm saying.
You know what the underlying statistical distribution is. So you know if it's Gaussian, the standard deviation would have one standard deviation that has 68% of the data. Two standard deviations are about 93, 95, etc. And it's distributed equally around. For some distribution, when you look at all right now,
No, that's,
it's a normal distribution.
yeah,
And so this is the measure of uncertainty. It might be 68% as well. I'm not sure. I let me check.
Let's check
Certain amount, it's typically what's used as a measure of uncertainty.
yeah, so I'm just wondering, should we say like a mean and uncertainty instead of mean and standard deviation, since standard deviation? The normal distribution as well.
But it's
Yeah.
the same, I mean, polling statistics go like this, for a metric model of counting or something.
Whether or not we call that a standard deviation or an uncertainty.
Yeah.
Well, yeah, I mean, for something where you have a probability of counting it or not in a subsample, I would say that that is an uncertainty. It's a counting uncertainty. It's your uncertainty of whether or not you get it or you don't,
Yeah.
right? But that's just in this application.
Okay.
All right, So-
Sorry.
so I'm gonna run this block, and I didn't suppress that either, so we can see here our counting uncertainty, right? So this is the number in each bin, sort of error bar magnitude, basically, is 21 for our smallest bin, going down to about 1.4 for our largest bin. So now what I'm going to do is throw those error bars onto the same plot that I made before. And we can see how those look with our data. So in log space, it especially is starting to become apparent that our relative uncertainty in those large size bins is pretty high, right? And this is actually a great time to just point out, we talked about it in terms of fitting the CDOM spectral slope a little while ago, but also fitting a power law size distribution to particle count data. You want to fit in linear space. You want to fit with a non-linear least squares fit to this, not a linearly squares fit to this, because this is full of uncertainty. You do it here, these low bins down here it won't be, Emmanuel used to say it's the tail wagging the dog. Yeah. You can do it. Yeah, yeah, so you could do it in log space, and you have to take care of it and put them into the weighting function. The simple fit script that I'm going to use does not do that. So we're going to do it in, yeah, but it really kind of, to me, you see it there. It's useful. Okay, so so far we've just been putting number of particles versus microns in size on our graph, but we're gonna now normalize to the volume sample, right, which we knew from the dashboard. So I'll divide the number of particles in each bin by the sample volume, and I'm also going to divide them by the width of the bin, because our size bins are of unequal width. There's much larger bins out here, the large sizes and the small ones. And when we do our power law fit, we need to have everything be equivalent across the bins. So we'll divide by the difference between the bin edges. That'll be the width. And then we're going to do the same thing with the uncertainty, so that we have the uncertainty and the bin particle count data in concentration and differential form. Okay. And then plot the normalized data. Okay. So this is what we're actually going to fit the power law to. Okay. We're going to end up getting a fit to this guy on, well, we'll fit it to the data on the left-hand side and be able to see our linear line that comes out on the right-hand side. Okay, so to do this, I'm going to use another script. So you can, and it's set up as a function. So I'm going to flip over to that and show that to you in a second. But what we're going to do is start off by, well, assigning a reference diameter. That's arbitrary, pretty much. You can test it. And then we're going to make an initial guess as to how many particles there were in a liter per micron in the bin centered at our reference diameter, which I set to 100 microns. So we're initially, this first term in XO is just saying, we're assuming to start that there are 100 particles in the 100 micron bin. And we're also going to assume our Sheldon 1990 or 1972 value to start with, that the size distribution slope is 4. That's probably wrong, but it's going to adjust those numbers. So this is our guess that goes in. And then this PSD compute underscore D naught is going to be a function that will do the minimization and then spit out the best fit parameters into the variable x1. And we're going to give this function the bin centers, so the vector with the centers of our bins. It needs the number, the differential number concentration. It needs our initial guess, and it needs the reference diameter. And this has to be on the search path or in the same folder. So let me. It shouldn't be. If your model is a good fit for your data and there aren't multiple ways that the model can fit your data in different regions, then it shouldn't matter. And that's a good thing to test. If you change those initial guess values and every time it converges to the same thing, that's a good thing to tell you, okay, it's a good model, right? If you get wildly different results or results that wiggle around a lot, it suggests maybe it's not a good model. So this function, here's the inputs. They have slightly different names. Like when you take your variables and throw them into a function, they can have different names inside the function. They just come in the same order. And there's a bunch of options for the fitting parameters here. You can read the comments to get into the nitty-gritty of that. And then the fmin search is going to minimize this function at LSQ PSD, which is down here at the bottom. So this is just a little sub function inside this script. And this is just a sum of squared differences. It's going to minimize that. Right, so we're putting in our initial guess. It's going to iterate until the function y is minimum, that it's at its minimum, and then that's going to come out in x1 up here. And then it will return that from this function back to my original script that I called it from. So if I go here and run it, we can see it's very fast. It's already told us. So here's the number concentration of particles at the reference diameter. That's like the magnitude parameter in our power law. And then it's giving us a slope of 1.799. So it's pretty flat, actually. And then we can plot that fit to the data. So we see this here. So the blue line is our power law fit in both the linear and the log versions. And you can see doesn't fit as well to the data that are out here because we fit it in linear space. So it's doing a better job fitting the bins that have the greater range. Okay. And we can also see that there's little differences, right, between our particle counts and this power law, which are actually useful, right? They might be telling us something about maybe there is a bloom of cells with particular diameter going on. This could tell us, hey, power law is a crappy model for these data. Maybe you need to fit a Gaussian to it, in which case you can just adjust the function inside that, that script that I just showed you and put in a different function, try fitting that instead. So there's a lot of steps that you can take from this point. But this is it. This is just a quick run through of how you might take these discretized particle counting data and fit them to a size distribution. And this is what all of these optical proxies for particle size would be comparing to, right? And have compared to and validating them. And a simple MATLAB thing, which I hope was helpful to some people. And yeah, just sort of stepping through things. So feel free to play around with that script or take out pieces of it that are useful and throw away the rest or whatever. You have questions? Yes.
With the linear routine that you use, is there a way to generate or like output generate uncertainties for your output?
The way that I do it with that is I actually I use a Monte Carlo.
Okay.
Routine.
Okay. So that's
So,
how you use it.
Yeah, so if I've got uncertainties on my data, I put those into, and then I say, okay, generate 1,000 realizations of my data and do it 1,000 times and then compute the standard deviation on the parameters. And I think we're doing a lecture on this later in the course, right? Right, Emmanuel? Yes? It's on the schedule. Or I'm doing a lecture on it. But the idea is we'll talk a little bit about applications of. That's one way.
Yeah.
It's the way I like to do it because it's conceptually it's jealous.
Yes.
Yeah. But I find it easier to just generate a lot of random numbers. And it should equal. Yeah. Okay. Other questions? Yes.
Comment, as you see when we talk about fitting a CNOP spectra with this, the detail of how you do it matters. Particularly if you want to compare you with some of the. So if you really could provide sufficient data and even better provide links to GitHub where you need where you go, so other people can recreate similar with your data exactly the same result. And with their own data result will get compared to yours. Because these strokes are different and Sheldon's even and so hopefully not widely, but it will be sort of we just want to make sure that you can data comparable. So all the details that go into the computations provide them to
One thing that I know about these data, because I played around with them a little bit in developing this code, is that if I change the bins just a little bit, this slope changes a lot. So this is actually a really bad example in terms of what you would want to publish. And part of that's because there's just not enough particles and they don't go, you know, if I took a week's worth of IFCB samples and pooled them all and did this, it would be much more robust, I think. Yes.
And this is beautiful, what you just said, because the one column is not even good.
No, it won't tell you if your sample wasn't large enough. And so you do need to play with your bins and play with your fit parameters and make sure that no matter what you do, you get the same answer. Yeah. But yeah, for particle size stuff in particular, having a large enough sample size, it's really important. Yeah.
And the other thing is, let's say you did a volume distribution. If you did volume distribution, volume distribution,
Mhm.
if it is really truly powerful distributed, you can do exactly what it should be for the volume, which is good. And you subtract 3 from the 1 for the number.
Mhm.
But what you find is when you do the volume distribution, it's not going to be really, it's not exciting.
Yeah.
Because power law is not a perfect model for this data. So how do you know, what you think affects your
Yeah.
and you tell the challenge with the volume, keep the volume, not keep the number.
You can, in fact, if you are interested in these kinds of data, I highly encourage you to take this script and go back up. You'll notice at the top, I read in and put into variables the area and the volumes of each of those particles as well. And then I ignored them.
See how
Reapply all of them.
how different it is.
Yeah.
People actually, you know, try to do something.
Yeah.
I recommend it.
There questions? Okay. All right, so it's lunchtime, I think, or in 5 minutes it is.
And the least output would be a volume. And not normalized by beams. But basically the default output of the software of the beams is the volume. So then you know the beams in order to normalize the beams, you want to move it to another one, you have to assume, you know, what's the size of my particle in this beam, you know, to convert it to its number and the area distribution.